In this video, we are going to discuss the second part of chapter 1.6 on trigonometry function. So we'll skip the beginning or the first part in this topic and go straight to the identity of trigonometric function. So we will begin talking about the identity and some information that you need to know about the identity of the trigonometric function. Until this stage, I suppose that every one of you should have understand how the 6 basic trigonometric functions are defined. And this identity, these trigonometric functions has relationships among each other. So in the following discussion, we will be telling you a few very basic and fundamental identities of this trigonometric function, and these are almost what we call a mandatory relationship that you must remember for your calculus class. Not only in this calculus class, but you may need it also in other fields of physics. So first of all, we begin by talking about the basic identity that the square of a cos add to the sine of a cos is equals to 1. So this is a very simple identity which could be straightforwardly derived from Pythagoras theorem. So as I mentioned in the class, if you have a point P that has the coordinate of x and y on the point, and you draw a line connecting the point P to the origin, then you define the radian measure in the positive directions, theta, in this case. So here the values of sine of the function is defined as the ratio of x over r, where r is the radius of the point P from O, and also cos theta is defined as, sorry, I think I made a slight typo here. So sine should be y over r and cos theta should be x over r. So here we have a point, and you can then simply drop down a line to the horizontal axis to make 90-degree with respect to it. Here also you can drop a line from point P to the y-axis. Then it is quite obvious that if you look at this triangle alone, this is a triangle which is a right triangle. So you can write down the relationships that relates the radius, or what you call the hypotenuse of the triangle, and the length of the base and the height of this triangle. So the height of the triangle is y and the length of it is x. Okay, so Pythagoras theorem relates r squared with x squared plus y squared. So to prove the identity of sine squared theta plus cos squared theta equals to 1, you simply set the radius of r to be equals to 1. So the argument or the discussion that will follow will be still valid when r is assuming the specific values of 1. So if this is the case, then the expression of r squared become 1, and x is nothing but just the r cos theta with a square. So it doesn't really matter whether the theta is in the first quadrant, second quadrant, third quadrant, or fourth quadrant. When you square, then the cos squared theta always is equals to 1. So is the values of y squared, which become r sine theta squared. And since we assume r to be 1, then we just drop off these values of r. So now you have this very general identity that the square of sine and the square of cos add up to be 1. So the identity is a direct result of the Pythagoras theorem drawn on the triangle that is displayed on the screen. So it is actually very easy to understand the identity of sine square with cos square. So remember the derivations of this identity is quite straightforward. Then we have a few more important fundamental identities involving cos theta and sin theta in the next slide. So the next very simple identity that you have to remember by heart is 1 plus tangent square theta is equals to secant square theta, and 1 plus cotangent square is cosecant square. So you don't really memorize this formula. You just memorize the identity that sine square theta plus cos square theta equals to 1, where I have used the shorthand notation of S to represent sine theta and the shorthand notations of C to represent cos theta. So you save my time and energy to write the identity in the short form of S to represent sine, cos is represented by C. So what you do here is that if you divide this equation by, say for example, sine square. So the whole equation, if you divide it by sine square, then S square divided by sine square become 1, and you have cos square divided by sine square equals to 1 over sine square. And you translate this set of equations into the definitions of, say for example, cotangent theta is the ratio of cos divided by sine, and then 1 over sine square by definition is cosecant square theta. Okay, so this term c square over s square is then just the cotangent square theta. 1 over sine square is just equals to, so let me write it down here, you have a 1 plus cotangent square is equals to cosecant square theta. So this is the identity of 1 plus cotangent square equals to cosecant square. So this is the identity. The other identity could be easily obtained by dividing these equations. Instead of by sine square, you divide this equation by cosecant by cos square. So if you divide this by cos square, then what you get is sine square divided by cos square, you get a tangent square. Cos square divided by cos square, you got a 1. The right hand side is 1 over cos square. 1 over cos square is by definitions equals to secant square. Okay, so that is the other identity. So from one single identity, you arrive at this identity and this identity. So you don't really need to memorize this one or this one. In case you have forgotten these two identity, you can always rederive it from the first identity by dividing it either by sine square or by cos square. So this is the identity that is derived from this identity. So we have so far studied discussed three different identities. The third thing I want to talk about is the law of cosine. So I'll talk about law of cosine because I need this law of cosine to derive other related identity. So what is law of cosine? Law of cosine is very simple. It is actually geometry, basic geometry that you learn from your form 2. I learned this geometry from form 2. So what you do is say you have a point P with a coordinate of x and y. Then this is origin, this is your y-axis, x-axis. So you just simply pick a point on the xy plane, then you draw a line from origin to the point P. Then you define the angle in the positive directions, theta. Okay, then you will start to write down the relationship between x and y and the angle. So the constructions to derive the cosecant theta is like this. So once you have jot down the point P, then you would like to construct a triangle. So let me say the triangle is to be constructed like this. So I would actually want to have a triangle where I have an additional point lying on the x-axis, say here. So I'll call this, to know what, I'll just call this point B. And the point B is made to be lying on the positive direction of x, so that the length of the line or from 0 to B, this line has a length of B. And then I'll call the length from 0 to P values of A. So here A and B are referring to the length of the point 0 OB and OP respectively. Then you draw a line connecting the point B and P. So I have a triangle that has the line A, length B, and also a length of this. So I'll call this length C. So you have length A, B, C of an triangle where the angles of theta is defined as this. So we would then write down, according to the Pythagoras theorem, the formula that relates A, C, B, and theta. Now, how do you draw that? So you draw that by recognizing that the length or that relates, say here. So you drop down the point P onto the point here. Then this is the distance between the point P and, say here, I call this, say, P prime, where P prime is a point line on the x-axis that is dropped down from the point P. So here the coordinate of this point P prime is actually the values of x. So the x here could be positive or could be negative, depend on the angle of theta. Okay, so the length between this B and prime, the P prime, is given by B minus x. Okay, it's not B plus x, but B minus x. And the height of the point P here is just A. Okay, so now you look at the triangle of this A. Okay, let me draw it here. You look at this triangle with a height of A, with a length of B minus x, and a length of C. So you can easily write down the Pythagoras theorem that says the C squared, which is the length of this hypotenuse, is just the sum of A squared plus the length here. Okay, so this could be then written down as B minus x squared plus A squared. Okay, so I think that is quite straightforward. Then we would want to express the values of x in terms of angle theta. Okay, so here the values of x is just equals to what? So the x is the values of let me see. So if this is the angle of theta, then this x value is just equals to let me see, it is equals to A times cos theta. Okay, so x, which is the coordinate of the point P here, is just the values of A multiplied with cos theta. So you would then substitute in the values of C squared equals to B minus A cos theta with a square plus an A square. So you open this up, you got C squared equals to A squared plus B squared minus 2AB cos theta. So this is what we call the law of cosine, that is given an triangle that has the sides of A, B, where the angle is defined between A and B to be theta, and C is the length of the third, what I call the third edge of this triangle, which is not necessarily 90 degree. Then the relationship between ABC angle is given by this law of cosine. In the special case where theta equals to 90 degree, then you get back A equals to C squared plus B squared, which is nothing but just the Pythagoras theorem. So before I switch on to the other slides, I just want to mention again the law of cosine here can be considered as a generalization of the Pythagoras theorem. Pythagoras theorem is a special case of the law of cosine when theta equals to 90 degree. So that is a very important and very useful relationship that relates the sides of a triangle and the angle theta that is defined between A and B. So with the law of cosine and sine, then you can derive another very important fundamental identity, that is the cos difference, the cos of the difference between an angle A and angle B. So this could be easily obtained by applying the law of cosine. So let me try to explain to you how you could obtain the law of cosine A minus, sorry, the law of difference between A and B for the cos function is given by cos A, cos B plus sine A, sine B. The derivation of this is actually quite easy if you apply the law of cosine onto an geometrical constructions of a circle that contains an tilted triangle. So let's say you just draw a triangle that is like this. Right, so then you have a point cut through the angle, cut through the circle, the perimeter here and here. Let me just call simply, I think this is just called P and Q. It doesn't really matter what names is it called. Then you have an angle, say here, say this is the angle of B, okay, a smaller angle, and then the angle A is defined to be from here to OP. Okay, so I call this A. So here I'm just assuming that A is larger than B, so that the difference between A and B is just the angle that I call theta. So let me draw the theta angle to be just given by this. So I have a triangle of A, Q, and O. Okay, so where theta is defined as the difference between the angle of A minus the angle of B. So with this knowledge, then we have to add in one more thing that I have not added in, that is the radius of the triangle R is assuming a value of 1. So with this assumption, then you can write down the law of cosine for this small simple triangle, that is the length of this. I'll just call this length as a PQ square, which is the length like this, that is equals to the sum of the R and R square and R square minus 2AB cos theta. So here this is the actually the C square in the previous slide for the cosine rule. Then this is equals to the side of R square, which is 1 square, plus the other side, which is also R square, minus 2AB. So here A is R, B is also R. So here this is just AB, and then times cos theta, where cos theta is just the angle defined between the two sides. So now we have a very simple relationship that relates cos theta and the length of P and Q. And what is the length of P and Q? So the length of P and Q, is could be easily work out based on the coordinate. So maybe I should draw the angle again on the circle. Okay, so this is a circle and this is a point P and this is a point Q. Okay, so this is the angle of theta. So here you see that this is the angle of A. Therefore, and it also has a radius of r equals to 1. Therefore, the x coordinate for the Q is simply equals to cos A. Okay, so cos A is the x coordinate of the point Q, and the coordinate of the y for Q is then sine theta. Sorry, sine A. Right, so sine A is referring to this height and cos A is this. So cos A, sine A are respectively the x and y coordinate for the point P. Then you can apply the same idea on the point P. The angle made by point P is B. So the x coordinate of point P is simply equals to what? It's simply equals to cos B, and the y coordinate is just sine B. Okay, so now we know the coordinate of the point P and Q. Then you can then use the geometry relationship between 2 points to write down the length of the straight line or the secant. Well, I mean secant, S-E-C-E-N-T. I think secant, C-A-N-T. This secant refers to a line that connects between 2 points, straight line. So the length of the point PQ is this term. Okay, so now we could write down the length of PQ. It is just equals to the difference between the x coordinate square between P and Q, and also the y square coordinate between P and Q. So the length of PQ squared is just the difference between the x coordinate of B minus the x coordinate of, sorry, not B, I think I should call this the x coordinate of Q and the x coordinate for P squared plus the y coordinate of Q minus y coordinate of P squared. Okay, so the x coordinate of Q is just this one, x coordinate for P is just this one. Okay, so then I can then write down xq to be cos A minus cos B, the whole thing squared, plus sine A minus sine B. Okay, so now I have obtained the length of PQ square in terms of cos and sine. So this could be easily simplified to cos square A plus cos square B minus 2 cos A cos B plus sine square A plus sine square B minus 2 sine A sine B. Okay, and you realize that the sum of, sorry, I think this should be like this. The sum of cos square A and sine square A will give you 1. Okay, so this will give you 1, where the 1 is coming from the sum of this one and this one. Likewise, for cos of B and sine of B, you add them up together, you get another constant of 1. Then you have 2 times cos A cos B minus sine A sine B. So that is the expression of PQ square. And what is PQ square? PQ square, according to the relationship that is written down based on the law of cosine, is just 2 minus 2 cos theta. So I'll now equate this PQ square to 2 minus 2 cos theta. This is nothing but just the expression that I wrote down by using the law of cosine. So now we are almost there. So here you can easily identify that the cos A cos B minus sin A sin B is just equals to cos theta. Or you simplify this further, cos theta is just equals to cos A cos B minus sin A sin B. And by definitions, the theta as I wrote it down is the definitions that is the difference between A and B. Okay, so here the cos of theta is just the cos of A minus B. So that is a true statement that could be easily obtained and proven by applying the law of cosine onto a circle that is constructed with a triangle encrypted in it, and then you define this angle theta, which is the difference between angle A and B. So you just try to see if you can reproduce this identity yourself. It should be. So I would actually advise you to try to at least go through this derivation yourself once or twice. When I was in my secondary school, I do this many times, and I can remember it until now. Okay, so that is the identity of cos of A minus B as cos A cos B plus sin A sin B. Oh, I think there is something which is not correct here. So I'm sorry. I think there is an sum of plus instead of minus. So here I have made a slight mistake. So we have a minus 2 cos A cos B minus 2 sin A sin B. So when I pull out the factor of minus 2, that would be a plus instead of a minus. So I'm sorry about my mistakes here. So I have now just proven that the cos of A minus B is cos A cos B plus sin A sin B, not a minus sign which I mistakenly wrote a few minutes ago. Okay, so I suppose now I have successfully shown you how the relationship of cos A minus B is derived. Now once you have derived the cos of A minus B, then you can easily obtain the other identity of cos plus B. How do you obtain the identity of cos of A plus B? You can do that by referring to the identity of cos of A minus B. Now, how do you arrive at the identity for cos A plus B from here? Is actually very simple. I just show you the steps which I'm going to do here. What you do is you perform an operation. So the operation that I'm talking here about is you look at the expression of B in this identity of cos of A minus B. So when you see a B symbol, you just replace it by minus B. Whenever B appears, you just replace it by minus B. Then the identity is then cast into the following form. So you have a cos A B become minus B. So here minus B become minus B, which is a plus B. And here you have a cos of A and cos of B. Cos of B under the operation of replacing B by minus B is then given by minus B. Okay. Then here you have a sine of A and sine of minus B. Okay, so now we have to get rid of the B and the sine of minus B. So you have to then understood, in order to get rid of this minus sign from the argument of cos and sine, you have to recall the mnemonic I mentioned in the previous slides. I think the mnemonic is the cos, is the what we call the cast rule here. The cast rule says that the the sine of the trigonometric function in each of the secant, right? So based on this cast rule, I can now try to simplify the expression of cos b. So what is cos b? Now cos b is like this. So this is C A S T. So cos b means you have an angle b, which is defined in the third secant. Okay, I think that is what you mean by b with a minus b. So here b is in the fourth quadrant. So here that means the sign of cos of minus b is positive. It's the same as the sign for cos b. Okay, so I write down this one based on the CAST or cast mnemonic. So this is just cos a and cos b. Okay, then I have sine a multiply with sine b. So according to the mnemonic, sine of negative b, that is a sine of b that lies in the fourth quadrant, is negative b. Okay, so that is understood from the cast mnemonic. So here this is just negative of sine b. So I'm going to rub this off and replace it with a minus. So that is how the cos of a plus b is derived, right? So you compare this, cos a minus b is cos a cos b plus sine a sine b. Then when you perform this operation, the same identity for cos of a minus b is now transformed into the form of cos of a plus b. So this relationship is derived based on the knowledge of this. Then this is just the rule or the identity for cos a plus b. So this is how you explain and derive the addition formula of the cos of two angles. Then you can also try to derive the sine of a plus b and also the sine of a minus b. I think, let me see here. I explained a little bit how the identity of sine of a and b can be derived. And also, I think in this slide, I explained to you, once you know the identity of sine of a and b, how do you arrive at the identity for sine of a and b? So here, I do not show you the derivations of sine of a plus b. So you go and try to read up how to derive this. It should be just quite straightforward. This is the hint of how to derive the identity of sine of a plus b, which is sine a cos b plus cos a sine b. So you would derive this identity yourself. What I'm going to do is I'm going to derive and show you the identity of the sine of a minus b. The derivation of sine of a minus b could be easily obtained from this identity. So what you do is that you start off from this identity of sine of a plus b, and then you perform the operation of replacing b with minus b from this identity. So by doing that, sine of a plus b is then become sine of a minus b. So here sine of a remain intact and no change. Cos of b become cos of minus b plus cos of a, that is no change, times sine of minus b. And applying the cast rule, cos of minus b, cos of minus b is just cos of b. So here I write down sine of a, cos of b. Cos a, sine of minus b, sine of minus b is just minus of sine of b. Therefore, this cos A sine minus B become minus cos A sine B. So that is how easy it is to arrive at the identity of sine of A minus B. Right? So sine of A minus B is just sine A cos B minus cos A sine B. So you realize that this identity could be easily obtained if you know what is the identity for sine of A plus B. So that finish up the derivations of the sine of A minus B. Then the last identity I want to show you here is the identity number 3, cos of 2 theta and sine of 2 theta. So these are the two identity that is of great importance and is very handy. So here the identity is cos of 2 theta is equals to square of cos theta minus square of sine theta, and the sine of 2 theta is just equals to 2 cos theta sine theta. So these are the identity number 3. So let me show you how this could be derived. This could be derived very easily if you can remember the sum of cos of A plus B, right? The cos of A plus B, as we mentioned earlier on, is just equals to cos A cos B minus sine A sine B. So by making A and B to be the same, and you call that angle theta, then cos of A plus B is just cos 2 theta, and you have cos theta minus sine theta, and that's just cos theta minus sine square theta, cos square theta minus sine square theta. So that is the identity of this one. There's one more thing I need to emphasize, which is not shown in the slide. That is, by using the identity that relates the square of cos and sine, that the square of cos and square of sine add up to be 1. So combining with this relationship, you can then cast the identity of cos 2 theta into the form of cos square theta minus 1, or 1 minus 2 sine square theta. So this is another very important identity which is not stated in the slides here, but otherwise it is still a very important identity. Then you have another identity of sine 2 theta. The identity of this could be easily obtained by referring to the identity of sine of the sum of two angles, which we just derived a minute ago. So that is, well, not derived this in a minute ago. I think you proved this yourself by using the instruction that is mentioned in slide number 20. So here the sine of A plus B is, according to the identity that I shown earlier on, is sine A cos B plus cos A sine B. So to arrive at sine of 2 theta, you just set A to be the same as B, to be represented in the symbol of theta instead of A or B. Then sine of A plus B just becomes sine 2 theta. Then become sine theta cos theta plus cos theta sine theta, and it's just 2 sine theta cos theta. So that finish up the relationship between sine 2 theta and sine 2 theta and sine theta cos theta. Before I proceed on, I just want to mention the importance of identity number 3. The identity number 3 has this importance. That is, for example here, this identity allows you to relate the product of sine and cos to be represented by a single angle of 2 theta in sine 2 theta. Okay, so here if you have expression of that involve sine theta or cos theta. So this is a product of two trigonometric functions. So effectively, this identity allows you to express the product of two different trigonometric function into a single trigonometric function of 2 theta. So this, the left hand side, is a much simpler function than the product of sine and cos. On the other hand, the cos of 2 theta to be expressed as 2 cos theta minus 1 or 1 minus 2 sine theta square. This has also a similar function. That is, if you have the square of a cos or the square of a sine, you can relate the square of a cos or square of the sine to a single trigonometric function of only cos 2 theta. Cos 2 theta is a much easier or much simpler trigonometric function than the square of a cos and the square of the sine. So again, the identity number 3 allows you to relate the square of a cos or sine with a trigonometric function of cos of 2 times the angle, which is easier than the square of the single angle. And this relationship allows you to relate the product of two angles, or the product of cos theta and sine theta, into a single function of just sine 2 theta. And these two identity straightforward. This is actually, to me, is nothing different from the double angle formula, right? These two are exactly equivalent to each other, except that here you just make cos square theta and sine square theta as your title based on this identity of this equation that I just written down. And this is a relationship that is obtained by slotting in the trigonometric function for sine square and cos square into the cos of 2 theta. So the summary is that we have discussed a few identities for the trigonometric functions, and we start off with the simplest one, which is the square of sine added to the square of cos. And this identity is just the different way of expressing the Pythagoras theorem on a circle. Once you obtain this one, then you can derive the other two identity involving tangent square and cotangent square by dividing the first identity by cos square or sine square. Then we express and explain the derivation of the cosine rule, which is the applications of the Pythagoras theorem onto this triangle. Then based on the law of cosine and sine, then we derive the other identity. Specifically, we derive the identity of cos of A minus B. Then from cos of A minus B identity, we derive the cos of A plus B identity. Then I didn't show you the derivation of sine of A plus B identity. I asked you to try to derive this, but I do show you how to derive the identity that involves sine of A minus B. And this is obtained by deriving it from the identity of sine of A plus B. In other words, if you understand or remember sine of A plus B, you could then remember sine of A minus B. Okay. Then finally, we derive the identity of cos of 2 angle that is related to the square of the sine and cos of a single angle. Okay, so that's all for this identity for topic 1.6. So thank you for your attention.